All right. Hello, everyone. We're back to this. Hope you had a decent weekend. It was a nice one for me. Uh, I I've got a list in my mind of things I'm not going to do, like click the table or squirm a whole lot. But bear with me. So you'll probably have seen from the email that on Wednesday we're going to have a Zoom meeting together, so we could just meet, see each other's faces, um, become responsible to the class again. I feel like I need that as much as you do. I did get responses from 5 of you from last week's assignment, which was to um, watch the lecture in conjunction with the slideshow and then answer the three questions at the end of the 2 periods. We'll have that again today. And I'm going to also respond to Aubrey's request to try to get this on Canvas as well, just so it's more formal or easier for you to access if that's easier for you. Okay, this is a follow-up in a more detailed explanation of how plants get fed or how nutrients interact with plants in their environment. First, some quotes from Haruki Murakami. He's a Japanese novelist, kind of famous these days, but he's good at kind of articulating the in-between spaces of life. Here's one. In this world, there are things you could do only alone and things you can only do with someone else. It's important to combine the two in just the right amount. Of course, it's very yin-yang, kind of Japanese Eastern philosophy to not really tell you how to combine the two in the right amount, but just to say that, balancing your solo time, your independent ambitions with your together times, your community time or community sharing is one of the secrets of a good life, right? He also goes on to say, it's not as if our lives are divided simply into light and dark. There's shadowy middle ground. Recognizing and understanding the shadows is what a healthy intelligence does. And to acquire a healthy intelligence takes a certain amount of time and effort. Of course it does, right? When we're kids, we learn about opposites and we learn about good and bad, and there's no in between. But as we get older, we realize that all adults know that there's only the in-between space, and that good and bad are extremes on two ends of a spectrum, and everything else is sort of blended in the middle. This is the case in gardening and farming all the time. There's never the perfect thing. It's always a little bit off, right? And there's never like the perfectly ruined thing. There's always something of value there. So we're always making these choices and judgments along a spectrum. And Murakami helps us to understand that that is what a healthy intelligence does. When we're unhealthy, we tend to look at things as extremes or as only this or only that. Like, this person's only bad, has nothing good to say, or you know what I mean? When I get in arguments, I'm being childish. It's like, you never do X, Y, Z, or you always say blah, 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 which of course is not true. There's always sometimes when you don't do those things, right? Okay, back into the world of farming reality. Remembering from last class, there are two paths for making nutrients for plants. There's the organic way, which is getting our nutrients from the breakdown or the decomposition of organic matter, whether that's manure or crop residues or animals dying or hair dissolving into the water making nutrients. So that's the organic way. And then there's the chemical soluble way. And this was the way that we discovered in the 20th century by synthesizing the minerals in an ionic or soluble form. So these fertilizers, these new fertilizers, you just add water to, and that becomes the nutrient solution. So the pieces of the puzzle are what we call macro and micronutrients. So the macro are the big ones: nitrogen, phosphorus, potassium. Those are the 3 numbers we see on fertilizer bags. and micro are sort of the other 15 or so, or 14 or so nutrients. There's 17 altogether, and there's a little graph later that kind of spells them all out completely. And then the organic path has more elements in play, because the soluble chemical path, this is all of those, that way of providing nutrients can provide just macro and micronutrients in soluble form. The organic form also has organic matter, which kind of contributes these nutrients and also supports other life in the soil. The living cohabitants that live off of the soil carbon or the soil organic matter, these would be like bacteria and fungi, some insects. And then organic methods pay a lot of attention to the structure of the soil. So this is how open the soil is on its own, or how easy it is to dig up or break up. A poorly structured soil, like a heavy clay, would be very dense and hard to break up with your hands. Or on the other spectrum, a very sandy soil would fall apart and never cohere. So good structure is a soil that coheres but breaks up easily. So here's what happens when we put a salt or a soluble fertilizer into water. In the crystal form, in this white form, salt is locked together tightly in sodium and chlorine atoms are locked together tightly. When it dissolves in water, the chlorine and the sodiums actually break apart, and they aren't connected anymore, and they are freely associating in the water. So this is a kind of graphic of what that looks like. In soil, it acts a little differently, and this is something you have to look at pretty closely, but certain soils have more charges on their particles, like clays and organic matter soils have more negatively charged sites where these positively charged anions could connect to. So we call that cation exchange capacity. That's the CEC there. So clay can hold more nutrients without them being rinsed away, like in the rain, whereas sand can hold less. And for that reason, it wastes fertilizer more. Like you have to put more fertilizer on a sandy soil. And we see this, it's pretty easy to see that sandy soils don't yield as well unless they're managed properly with their fertility. So this is something you can look at on your own, try to make sense of it. And this is kind of a visual breakdown of where fertility would come from in the two systems. This is I think it was a nitrogen factory. So this is making nitrate or ammonium and nitrate. So yeah, it looks pretty weird, but you've probably seen places like this. This is weird in a different way, but this is how decomposition happens and soil structure and tilth happens, and all this organic matter breaks down and provides nutrients for this web of life. And then same side on the left side here, this is a soil that's managed with chemical fertilizer, which tends to over-rev the soils quickly and burns out the organic matter. And this is soil managed organically, which tends to build organic matter because it needs it for its fertility. So that blackness, that difference there is soil organic matter. And this happens pretty quickly. Within a generation, soil that looks this good can become soil that looks this poor under soluble conventional management. So here it is. I won't go over again, but this is macronutrients. And the way we understood this, the way we found this out initially, was that the scientist Leipzig, a German scientist, burned plants and really accurately counted what chemical constituents were there, which minerals were there, and found that nitrogen, phosphorus, and potassium made up over 90% of the ash that was left over. And this is just like in the Inquisition, the scientific church would burn people at the stake or torture them with fire to get them to tell them the truth as to whether they're witches or not, right? So it's kind of an old path for understanding, and it certainly did yield some important truths for understanding how plants grow. But it's weird that it's the same way that they would try to get information out of witches. I think, let me check my time here. Okay, we're good. We got 5 minutes. The micronutrients are much less by weight, so they're in the 10% of the weight of the plant, and we'll see things like copper, iron, manganese, zinc, boron, chlorine, molybdenum, calcium, magnesium, sulfur. They're sort of the biggest of the micros, or some people put them as the smallest of the macros. That constitutes all the minerals that are essential in a plant. Again, you could check this out on your own. And here we see, this is a pH scale. So this shows us pH 4 to 10. And we see the optimum zone for getting the most in the green zone, the most availability of each of these minerals, is 6.5 to 7.0. We see iron a little bit out of the optimum range there, and molybdenum, and those sometimes need to be supplemented. But all the big ones, all the secondary big ones, and a good deal of the micros are the most available between 6.5 and 7.0 pH scale. So that's where we target our soils, and that's where we want to get our soils to. If they're really sour, like blueberry soils, blueberries can grow in 4 to 4.5. They can grow way over here because they're adapted to it, and they can access those nutrients in some ways. So blueberry farmers tend to keep their soils strongly acidic. Conversely, asparagus can grow pretty well at 8 to 8.5, and they'll modify the soil pH to get it to grow asparagus better that way. But this is a pretty cool chart to kind of show why 6.5 to 7 is the optimum pH for most soils and most crops. This is like even somewhat troubling for me to look at, but if you want to dig in a little deeper, this is a full table of all the required macro and micronutrients, the minerals that plants need in their fertility base, and where they come from, where they can come from in terms of fertilizer. It says whether they're positive or negatively charged. So all the green ones are positively charged, all the blue ones are negatively charged. And some notes here are kind of interesting. So that graduates us to the living part of the soil, the part of the soil that isn't required by plants, because there's no soil carbon in, for example, our hydroponic system. That's just liquid nutrients. But in a soil-based system or an organic farm or garden, soil carbon is the most important thing. It's all that was once alive and is now still alive. So this breaks down, less than 5% of it is alive. So it'd be like all the bugs that are still walking, all the bacteria that are still being bacteria, all the little animals and plants. That's less than 5% of the total weight in the soil. There's a slow turnover. This is kind of humus, wood chips, little particles that are decomposing over like a 20 to 40 year timetable. And then there's over half of the soil carbon is very, very slowly breaking down. And we've learned quite a bit about this part of it, and it's a really important part. Biochar, like there's a way to make charcoal that creates this material that takes a long time to break down. And in Brazilian rainforests, they have these soils called the terra pretas, and they are soils that were made by humans burning very cool burns in the rainforest, and that created soils that were durably and almost permanently fertile in a place where soils tend to be kind of weak and infertile, like the rainforest. Some of these living cohabits, I've got some pictures too, but these are root colonizing bacteria. These are like the bacteria that grow inside of legumes that make the nitrogen. These endomycorrhizal fungi, these are ones that grow in the plant, and then these sort of larger creatures that move around like protozoa, tiny insects that chew on the roots and stimulate plant growth. Here's a picture. See, these are kind of a diagram of arbuscular endomycorrhizae and then ectomycorrhizae, ones that grow on the outside of the root. And this is what they kind of look like, these fuzzy patches. Lastly, tilth.